Thank you. Like was said, I would like to talk to you today about in programming, low-level programming on the EVM and how to improve it. So to jump right into this, some background. We presented a project called Warp at SBC last year, and what Warp is it's essentially a design for an on-chain order book, and it's unique in that it uses what we've dubbed a logarithmic matching engine. Traditionally, matching engines for order books ran in linear time, but our construction runs in logarithmic time, and I'll briefly go over a bit of that. But what I would like to focus on is the data structure we use on chain and how we implemented it. Because in the SBC's talk that we gave, we briefly mentioned that it was implemented in EVM, but that doesn't really do it justice. So this talk is sort of a continuation of the talk we gave in August, and there's a QR code and a link there for people who would like some more information on that. Like I said, Warp is not written in EVM. It's written in a superset of EVM that we've named Joule. And we believe that this offers more optimal gas usage, more gas efficiency, at least for our use case. But before we get into that, I would like to cover the current EVM ecosystem in terms of programming languages that you can actually use on the EVM. So the EVM language ecosystem biases you towards high-level languages. So everyone knows about like Solidity and Viper, basically. Those are probably the two most widely used ones. They give you a lot of very high-level features, a very similar set of high-level features. Viper has a slightly more restricted feature set. But it more or less gives you almost everything you get in Solidity. But what you'll notice is you can't really think of very many low-level languages on the EVM. Not many people actually write production smart contracts in low-level languages. So to go over Solidity, the high-level features it gives you are types and memory-based structs, and that memory-based structs is important. I'd like you to remember that because I'm gonna get into that later. Memory versus stack-based structs. So it gives you automatic storage management. You know, you have like arrays and mappings, and the storage keys. So in the EVM, there's opcodes, right? There's sload and store. And store, basically, you can provide a key and a value, and it pulls from the stack, not from the heap. So these are 256-bit words that you're passing to store. So what Solidity does in the background is it has these things called slots, and it'll basically hash a bunch of stuff together to create a key to pass into the store, and it handles this automatically in the background. There's a lot of stuff going on there that the average programmer might not see. The other thing it does with storage is it automatically packs and unpacks structs for you. So when you pack, let's say a 32-byte struct, if it can be packed into 32 bytes, it results in one store, one sload. If you have a struct that's bigger, what Solidity will do is it'll actually split it up into multiple stores, into multiple storage slots. And this could be like a foot gun for somebody who's new to Solidity and doesn't understand that it is multiple stores, because I mean each store, that's expensive. It's a lot of gas usage, and especially to people who are new to the language, that can be kind of a foot gun. It has automatic arithmetic checks. It didn't always. People in the past used like the safe math library, but this is sort of the opposite of a foot gun, right? It protects you against overflows, underflows, divide by zero, stuff like that. But if you do want to do anything like really low level, there are certain cases where an arithmetic operation is not going to overflow. So in many situations where somebody is doing something low level, you'll just see a giant unchecked block where they do all their arithmetic that they know is not going to overflow. The other thing Solidity does for you is automatic stack and memory management. So this is definitely one of the nicer things that Solidity does for you. You don't have to worry about memory management yourself. If you're just writing raw EVM code, which I'm going to get into a second, UL, you basically have to manage memory yourself. You have to create a memory layout, set up like a memory guard if you want automatic switching from the stack to memory. It's kind of a pain to do that manually. So it's nice that Solidity does that automatically. And Solidity also has like automatic ABI encoding, decoding for call data and events. And that makes things really nice. On the EVM, there's basically just a convention for how you're supposed to encode call data. And Solidity, and all of this applies to Viper too. They all do this basically the same. I think there might be like one minor difference between Solidity and Viper and how they encode things. And then there's like various other behind the scenes magic. So that's Solidity. That's basically the status quo for programming languages on the EVM. They're typically very high level. So what do we have in the way of low level languages? So what's interesting about the Solidity compiler is it does expose a low level language called UL. And a lot of people have seen this language, and a lot of people might just refer to it as inline assembly because that's where you see it most often, is in an inline assembly block inside Solidity code. But UL can also be used as an IR target for Solidity itself. Solidity code can compile to UL, and then the UL optimizer is run on the generated UL code, and that is ultimately used to generate EVM bytecode from. I think this is like an optional backend for Solidity right now. I don't know if it's been enabled by default yet. But that's kind of cool because UL is an IR target. That means basically anything can target it, right? You can create any language you want on top of it, compile it to UL, and call out to solc. And solc will do all the difficult optimizations for you. And UL is now very stable. There's not many changes being made to it. So there is another low-level language in addition to UL. It was an attempt to extend UL to add some much-needed features if you were to use it for a standalone language, and that was called UL+. It's now defunct. I don't think it's maintained anymore. Maybe somebody could correct me on that. But that added a few features. So let's just go over plain UL first. So UL, aka Solidity IR, a little bit different from Solidity. There's no types, there's no structs, there's no automatic storage. You're going to call sstore, sload. It's all just stack items that you pass in 256-bit words. Doesn't do any struct packing, unpacking. There's no arithmetic checks. Everything's unsafe. It's manual memory management. The memory management is really annoying because you don't actually have any kind of pointer syntax like you do in C. You're just like passing integers into mstore, mload. There's no easy branching. You can do if, but you can't do else or else if. So that's really, to anybody who's written UL code, I think most people would agree that that's very annoying. That doesn't exist. There is a switch statement, which can basically be used to emulate else or else if. And probably one of the biggest impediments to actually writing a full smart contract in UL is there's no easy way to expose external functions. And if you want to do that, you basically have to like calculate the signature, the function signatures yourself, create a giant switch statement as an entry point into the contract, and then basically pick which method you want to call based on the call data that was passed into the call. So UL Plus attempted to iterate on this. They added like consts, enums, like a few other things. And they did attempt to add structs. It was a very primitive mechanism for handling memory-based structs. So why use a low-level language? Why use a low-level language in the first place? So there's a time and a place for high-level languages, and there's a time and a place for low-level languages. There's a reason we have Golang and we have C. Sometimes it's personal preference, and sometimes there's real reasons behind why you would pick a higher or low-level language for whatever you're building. So the features and behavior that Solidity has are very nice, but they can be a drawback sometimes. So like I mentioned before, people writing Solidity code where it's nothing in this code block is going to overflow. So it's you have to put unchecked everywhere. There are many situations in Solidity code. You'll see this all over in Solidity where, people just put inline assembly blocks everywhere. Because there's just certain features that Solidity doesn't expose or doesn't expose well and is better handled by the low level. So what we noticed when we were working on Warp, and the reason we were sort of attracted to lower level languages, what little there's only basically Yule, is that Warp puts a very complex data structure on chain. And we ultimately found Yule to be better suited for this. Just low level programming in general is just, in my opinion, more suited for complex data structures that need to be efficient. So yeah, our project led us to seek out some kind of low-level language. But basically the only thing available was Yule, so we attempted to use that. But before I get into that, I would like to talk about Solidity and what sort of drove us away from Solidity. So the Solidity compiler, I can't emphasize this enough, is an amazing achievement. It's very hard to write a compiler. I mean that with all sincerity. Just all the very complex optimizations that they put into it is very impressive. But the Solidity language itself can throw you a curveball every once in a while. And I would like to show you this as an example. This is an example of a breaking change that went into the Solidity language in 0.8 of the compiler. So yeah, I mean, you can take that as you will, but basically what it's doing is it's redefining a lot of the type semantics of the language. And this is bound to happen if you have a language in development that has a complex type system associated with it. And it's continued there, and it goes on even longer. But you basically have to relearn the semantics of the language to figure out how to use it again. So Yule is different. Yule doesn't have a complex type system. It doesn't really have a type system at all. Everything's just a 256-bit word. And because the EVM is it's a very specific use case, right? It's very domain specific. So it's you could try to write a C compiler for Yule for the EVM. But and I actually tried to do that at one point. I gave up very quickly because it's not an easy undertaking. So that leaves us with Yule. And Yule's not a bad option. It already exists. It's well tested. It's well optimized. And because it's very simple, it doesn't have complex type system, it's unlikely to be the subject of any change and any major breaking change. Especially if other languages are targeting Yule as an IR target, there's problems with just pulling the rug out from under all these other projects that are using Yule as IR. I think FE, the Rust-like smart contract language that's currently under development, also uses Yule as an IR target. So Yule was clearly intended to be a language just for IR, which is why it doesn't have nice things like structs and memory management and all this other stuff. But maybe like Yule Plus, we could give another attempt at making it more usable as a standalone language. Okay. So we ended up making a language called Joule, which is a thin layer on top of Joule. So it's basically a superset of Joule. So it allows for packed stack-based structs. And this is interesting because this differs from basically every other EVM language, which has memory-based structs. Like it loads it into memory, everything is an mload store. In our language, Joule, everything's a stack element, and it's essentially it's similar to C. It's essentially a collection of C bit fields. You could think of it that way. It's all bitwise operations you're doing on one stack item, one word, and 256-bit word. So it makes use of Joule's unused type grammar to designate a struct type for a variable. I think this type grammar was in Joule originally because Joule was also meant to be able to compile to WASM at one point. I think that was just ripped out. But it needed types for WASM output. I don't think it's used anymore, but it's still defined in the grammar. So we can reuse that type grammar to designate a type for a variable. In this case, just structs, because that's the only types it really gives you to structs. Include statements for multi-file projects. Macros as part of the language is not a preprocessor like C. Originally, I wanted to have some like C-like preprocessor, but I realized it's a bit nicer if it's not a preprocessor and the macros are just like part of the language. It has built-in functions for a lot of common operations, like require a search, SHA-256, like all the precompiles. It has syntactic additions like if else and else if. So we finally got that, and that basically just transpiles to a switch statement. And then there's a number of Solidity idioms, which I'm calling Solidiums, for easy definition of external functions, which I will call methods. In Joule, we call external functions methods because the function keyword is already used for Joule, the Joule functions. So there's sort of a collision there. So external functions, events, errors. So I would like to show you an example of a Joule smart contract. So what this is we're basically creating a token called foobar. And in order to mint this token, you have to burn some ETH. You send Ether to the mint function, and it will mint for you two tokens, foo and bar. And we store that on the user val struct. And as you can see, we have a method here on line 6, which is basically an external function. And the function parameters, the modifiers, they're all very similar to Solidity. There's like the payable modifier, or we'll just go, it's like the mutability or something. I can't remember. And then there's also an easy way to parse call data. You can do call data 2, and that automatically gets transpiled to a call data load. And then on lines 10 and 11, you'll see member accesses of a struct. So what that's doing is val on line 8, that is on the stack because it's the result of an S load. So on lines 10 and 11, what those basically get transpiled to is they are bitwise operations. It's like a shift and an and to actually get these members off of the struct. And then we do some arithmetic on it. And then we reinstantiate it as another struct and pass it back into storage. And at the very bottom on line 19, we're calling something called method.select. And what that does is it tells the compiler to generate a switch statement based on the methods that you defined. So in this case, mint. And that will be the main entry point for the contract. So when transpiled, it basically looks like this. And I hope you all can see that. Basically looks like this. So the method.select is now basically on line 10. And it generated this very ugly looking switch statement for us. It verifies the call data size to make sure people aren't passing in too much, too little. It also verifies the width of the parameters. On line 20, you can see it, checking that there's no top bit set on the address that's getting passed in. And then the method itself. So if we look at method mint, it automatically transpiled that call data.to to call data load 4. And then foo amount and bar amount, as you can see, they're just bitwise operations. And then so this isn't actually a full contract. For brevity, I sort of took out a lot of the object syntax that's inherent to EUL. So this is just basically like the main runtime code block you're looking at. There's also a built-in called safeadd 128. That's also excluded for brevity. But what the compiler will do is it will inline this function safeadd on lines 6 and 7 that you see on line 6 and 7. Just to, and that's just to check for overflows for 128-bit integers. And then on line 8, we reserialize the struct and put it back into the storage. So it's very simple. You don't have to do any memory management here. There may be some overhead, which I will get to in a minute, but this is typically the pattern of smart contracts, is that typically what you're doing is you pull something out of storage, you update like 1 or 2 values, and then you put it directly back into storage. Like it doesn't make all that much sense for structs to be overly featureful and be stored in memory. And this is what we discovered really quickly when we were writing our smart contract, is that we don't really need memory-based structs. Like that is something we were considering when we were just writing raw EUL originally. But we ultimately ended on these stack-based structs, these bitwise structs. And they seem to work really, really well in practice. You can also get an ABI file. This is another major impediment to writing a actual contract in EUL, is that not only do you have to generate the function signatures yourself, you have to write an ABI file by hand, and nobody wants to do that. It's also very unsafe. What if you get something wrong? And going back to the original example, this could be written much more simply. But the reason I didn't write it more simply, so here's the simpler version. Here's how you might implement it, right? You're on lines 9 and 10, you're pulling foo amount, and bar amount off the struct directly. And then on lines 9 and 10, there's a member assignment. So you're assigning it directly back to the members. So this is kind of interesting, but because these are stack-based structs, what's going to have to happen on line 9 and 10 is that the bits for foo amount and bar amount are going to have to be zeroed with bitwise operations. And then the results, the R values on 9 and 10, are going to have to be ORed onto val, which basically looks like this. And this is why I didn't show you guys this slide originally, because it's hard to look at. So there is some overhead when you're writing directly to structs, because it's going to need to zero the bits. But there's ways around that. In many cases, it might just be faster to like reserialize a struct. So this is something you do need to be aware of when you are using stack-based structs. So here's another example. It's the simple version of foobar token again. And one thing I'd like to point out here is I mentioned the slot stuff with Solidity and how it hashes everything it hashes storage slots together with a bunch of other things to like create these mappings, and it does a lot of fancy stuff to handle storage keys for you. But using this struct construct that we have in Joule, these stack-based structs, it's actually very convenient to create storage keys for sload and store. So you can basically use sload and store the same way you would use like any key value store. You can avoid key collisions yourself by, assigning a prefix to each different type of key, as you can see on line 2. And I would also like to point out, this is just an aside, but we use the arrow syntax for structs just because dot is a valid character for an identifier in EUL. Call data.to, that's sort of different because call data is like sort of a reserved word in EUL. But that's just an aside. So here's an example of an ERC20, an excerpt from an ERC20 contract. This is basically an ERC20 transfer. So as you can see, we do allow you to declare events as well. And what you might notice on line 14, when you actually emit the transfer event, is there's sort of an extra argument in the beginning. And that's because there are two index parameters for transfer, but there's one non-index parameter for transfer. So that's going to need to go on in memory. So any sort of built-in function or language construct that affects memory inside Joule, you have to pass in a pointer as the first argument. You have to pass in some kind of scratch space for the compiler to use to actually put that memory on. And here we're just using pointer 0 because we're not using any other memory in this function. You could come up with a more complex memory layout if you want to, but the compiler makes no assumptions about about memory or how you're going to use it. And likewise, the on line 20, the returns sugar that we have right there, the first argument is basically a pointer for scratch space. And then I put the if else in here just to prove that we can do it. We finally have else inside Joule. Here's a different way to write it using macros. So Joule supports macros, and yeah, we create the update macro, you pass in an address, an operation, and then you can just call update, and it will actually emit the exact same code as what's inside this if block. I don't know how I'm doing on time, so I'm going to try to hurry this up. So yeah, stack-based structs. So yeah, Joule biases you towards using a stack over memory. And I sort of briefly went over this. Most smart contracts, you're usually just pulling something out of storage, changing one thing, and then writing it back to storage. So it doesn't really make sense to have like really over-engineered structs unless you're doing something very interesting. The other thing is by keeping structs on the stack, you sort of have forced awareness of the fact that you cannot go over 256 bits. If you go over 256 bits, that's an extra S store. And it kind of reminds me of the days in JavaScript before we had like promises or async await. You had to just use callbacks, and callbacks were really annoying to use. But I always thought there was some benefit to having that annoyingness, that cumbersomeness associated with it, because it makes you overly aware that whatever you're doing is doing I/O. Like this operation may take forever to complete. You have no idea how long it's going to take. So it made you aware that you're doing some kind of heavy operation, and you need to be wary of that. And by the same token, Joule and Yule sort of enforce this. They don't hide this from you like Solidity does. Like if you're doing two S stores, if you have to do two S stores, you will know it. And because every struct is just a collection of bit fields, Joule can actually do things Solidity can't. For example, using very strange integer widths. And that might not sound like a feature to you, or might sound like an anti-feature, but we've actually run into a situation where we needed to use a uint26. Don't ask me why, but every bit counts when you're dealing with storage on the EVM, because it's the difference between 5,000 gas and 10,000 gas. So it's like every bit matters. And I've never really worked with a system where it's like you're desperately trying to find one bit to fit on a struct. And this is something Joule does really, really well, is that you can always find that last bit that you need on a struct to get something into one S store. So now I'd like to talk about Warp. I briefly mentioned this in the beginning. So Warp uses a very complex on-chain data structure for its order book. So I'm going to give a brief description of what Warp is and how it works. So Warp is an order book, and the problem with order books is you need a matching algorithm. And most order books match by price time priority, and basically what that means is prices closer to the top of the book are taken first, with time as a tiebreaker. So the problem with this is many orders can be placed at the same price. One order may potentially fill an infinite number of resting orders or prices. The traditional way of doing this basically runs in linear time, and I'll briefly get into that. And linear complexity is unacceptable in a decentralized system like a blockchain, especially when n is unbounded. Or I should just say when n is unbounded. And the reason for that is you can hit the gas limit, right? Your smart contract just stops functioning depending on the state of the data structure. So the traditional order book, and this was covered in our SBC stock, but basically the traditional way to write an order book is basically like this. You use a self-balancing binary search tree or a radix tree. Usually it's a red-black tree for price points. So every node in this tree is a price. And then at each node, there's a linked list of orders. So it has some decent properties. There's log and insertion, O1 if the price already exists, O1 cancel, O1 price lookup. But the problem here, like I mentioned, is linear matching complexity. So when an order matches, let's say it matches a million other orders or a million other prices, you have to iterate through every single order one by one to fulfill them. So this is completely unacceptable for a blockchain. And that's basically the reason everybody writes order books like this, as far as I can tell, is because there was one blog post that says this is how you should do it. There's very little literature on how to write an order book. If somebody could find literature on how to write an order book, actual academic published literature, I would be amazed, because I've spent 2 years looking now and I haven't found it. It seems to me most order books are like trade secrets, and it's not published very frequently. So yeah, that's basically the traditional design. A lot of projects on GitHub, when they're open source order books, use this design, but we can't use it for Warp because you're going to hit the gas limit. What somebody can do is they can DOS the order book. They can put a bunch of tiny orders at the top of the book. Somebody takes those orders, it goes above the 30 million gas limit, and then your contract is essentially bricked. So this is what the traditional order book price tree looks like. Is each node is a price, and each node points to a linked list of orders. So to avoid linear complexity, we need to be a little bit more clever about how we arrange this data. We can't do it like this. So in Warp, we use something called a double sum radix tree. It's basically a sum. It's a sum tree, but we store two sums on each node. So it utilizes a radix tree of price and orders. And leaf nodes maintain two extra fields, quantity and value. So quantity would be the amount in the left-hand side of the pair, the base. Price is the quote. And then we define value as price times quantity, and the result should be in quote units, right? So if you have like a BTC USD pair, the value is in USD because it's price times quantity. And then internal nodes maintain some quantity and some value. It's pretty self-explanatory. It's the sums of, the node's quantities or the children's quantities or values. So this has very different properties from what I showed you before. It has login, insertion, cancel, price lookup, and it's okay worst case. But the important thing here is it has log n matching. Okay worst case, and O2K minus 1, in worst case in terms of traversal during the actual matching that happens. Technically you could say it's not log n matching, it's not log n insertion. Like radix trees are typically like OK, where K is the depth of the tree, but the depth of the tree is logarithmic. So because of this, we call this a logarithmic matching engine, even though it's a radix tree. So I would like to show you. Oh, okay. So yeah, this is basically what it looks like. And this was covered in the SBC talk for anybody who's interested. So it's a pretty complex data structure. It's all these nodes need to be summed together. More importantly, they all need to fit inside 32 bytes. Just because if these were like 64 bytes, if they require 2 S stores per node, we're constantly summing up and down this tree when we're changing things around. So I would like to show you sort of an excerpt from our Joule code, which implements this data structure on chain. And it basically looks like this. So this is sort of what I was pointing out before, is so we're inserting an order, and we're inserting a node into this tree, and it has quantity and value, and that needs to be summed up with every node it touches as it passes down its path down the tree. So this is kind of what I was hitting on before, is it's very clear all we're doing here is pulling something out of storage, changing two values, and then putting it directly back into storage. And it's a 32-byte SStore. So it all works very well with our data structure, with a tree data structure. Joule has served us very well. So what to take away from this? Joule tries to work with the EVM constraints, and the constraints being, how storage works, essentially. We work with the constraints rather than abstracting them away. And while Solidity is good at what it does, there is a time and place for low-level programming. One thing I would like to point out, and I don't think many people have pointed this out, is I do think in the future it's reasonable to suggest that there be SStore and SLoad opcodes that are not restricted to 32 bytes that maybe pull off the heap instead of the stack. And the reason for this is forcing programmers to split up their structs, to split up 64-byte values into two SStores is actually harmful to the network, because now there's more leaves inside the Patricia tribe. And that's actually where the real bottleneck is coming from, right? All of this needs to go into LevelDB. And if the network is forcing programmers to split up structs, you're going to end up with more leaves in the tree, more internal nodes. It's probably better to increase that limit so that people don't have to actually chop up their structs into multiple SStores, and it would probably be a lot less load on the network. And in that regard, Solidity and Viper might be more appealing if that feature existed, because it's like now you don't have to chop up your structs. It does seem to me there's like a slight disconnect between what Solidity wants to do and what the EVM wants to do, but I don't actually know the history there or how that came to be. But nonetheless, all that said, the EVM is suitable for complex on-chain data structures either way, and it works. It works well enough. It works well enough that we can actually do what we want to do with order books on chain. And this is the EVM works well. This is our data structure, for example. We can't put it on Solana just because of the way storage works on Solana. You have programs which have storage, and you need to pre-commit to every program address before you, it would just be absolutely impossible, because we're touching all of these different storage slots as we're traversing down the tree. We have an implementation. It's up on GitHub right now. There's a QR code for it. If anyone wants to play around with that, give us feedback, post issues. It is very experimental, so expect features to change. Things might break. Use at your own risk. We don't recommend you using it for anything intended to be used in production right now. And that's basically it. If anyone has any questions, feel free to ask. Okay. Maybe I'll leave that QR code up just so people can grab it. But yeah, that's it then.